Okay, so in shallow, what is a TPM? It's sort of like a smart card. Usually it's implemented on a smart card chip. Usually it's very cheap. As a matter of fact, our design mandate said we had to design something that was very cheap. Occasionally you'll hear people making wild claims about TPMs being able to do all sorts of things like watch what you're running on your computer and making decisions as to whether or not it's going to allow you to run that application on your computer. Believe me, if we could do that on a cheap chip, we'd be doing much more important things with our expertise. Our design mandates were very simple. If it can be done in software, do it in software. Hardware is expensive, software is cheap. Backwards compatibility is really important. If you've got security software already out there that's designed to do things and that the hardware is going to also be able to do, we want the interface to allow it to do that. Is this echoing terribly, or is it just me? Okay. And we want to get synergy from the fact that the TPM is actually attached to your platform. This is different from a smart card. Smart card is obviously separate from your platform. And so when you think about authentication, normally you think of what you know, your password, who you are, biometric, what you have, which normally people think of as a smart card, but the PC is a thing that you have. Why should you have yet another thing that you have? And it's really important that we be able to use the PC as the thing that you're identifying, because if you're an IT organization, you want to know which PCs are trying to get into your network. So we're going to use the fact that TPM is attached to the platform to allow you to identify the platform. The IT organization knows what it put on your platform. It's the one that put the software, the kernel, the updates, the antivirus, all that type of thing. And so it's very important to them to be able to identify it's one of their platforms. So we're going to be able to use the TPM to be a proxy for your platform, so that's nice. And the last thing you hear about authentication, and you don't hear about this too often, but it's the state something's in. So you think about the time clock at a bank that only allows the safe to be open during business hours. TPM can give you some of that kind of authentication as well. It can, as we'll see, only allow keys to be used if the TPM itself is in a certain state, which is kind of a cool thing. And since I was in the PC company at this time, working for IBM, one of our design mandates was the design should not make it hard for people to upgrade their platform, because we were selling platforms. Really, really important to us that people not feel like they couldn't buy a new platform. So what can a TPM do? Well, even TPM 2.0 from 50,000 feet looks pretty much the same as 1.2 in the following ways. It has a random number generator in it. And a random number generator is good for a couple things. One is when you have an OS. The OS uses random numbers for all sorts of things. Most protocols require a random number. Random numbers used to ensure freshness. Random numbers are used for creating keys, so the TPM, when it creates keys, needs to have its own random number generator. And indeed, Microsoft has allowed its random number generator to be seeded in part with a TPM. And a 3 years ago, Dell released code that allows Linux to update its random number generator from the random number generator in the TPM. I always assume that you use multiple things for randomness in your seeding, but this should be one of them, because it's free. It's there, and what can it hurt? I mean, it certainly is going to help. And if you get a whole bunch of things and you turn them on and generate keys based on software randomness, where did that entropy come from? These things got shipped out of the factory, you turn them on. They don't have any time to get any entropy from anywhere. But they do have a hardware random number generator. That gives you a good place to get some entropy. So you really should be using that as one of your sources of entropy. There are a bunch of keys that the TPM allows you to have, and different kinds of keys, and we'll talk about each one of these in the following slides. But storage keys, and the reason for this is when we asked our crypto experts at the time, how many keys do we need to be able to store in this thing? The answer came back more than 3. And more than 3 means that we're not going to have enough memory inside this thing and keep it cheap to store them all inside the TPM. So therefore, we had to have some mechanism to store the keys outside the TPM and then import them into the TPM when we wanted to use them. And so as a result, we've got storage keys in the TPM. TPM knows the private portion, and the public portion is used to encrypt the other keys it generates and stores them outside the TPM where storage is free. Well, perhaps our storage experts wouldn't agree with free, but believe me, when you're talking about a couple K of memory and people have terabyte drives in their pocket, that's free. On the other hand, NVRAM inside the TPM is very expensive. In 1.2, all the integrity was done with SHA-1 hashes. Somebody asked me a while ago, why did you pick SHA-1? Well, at the time, our other choice was MD5. Aren't you glad we didn't pick that one? So, SHA-1 is still pretty secure, particularly the way we've used it. I don't think there have been any attacks against that. But TPM 2.0 is moving to other hash algorithms. Symmetric in 1.2 is a mixed bag, but you can't use it for bulk encryption. In 2.0, that's been relaxed. And keys can be what we call migratable or non-migratable. And by that, we mean that some keys are generated inside the TPM and will never leave the TPM in an unencrypted state. You can't even leave encrypted in a way that anything other than the TPM can read. And that's because what a friend of mine, Dave Safford at IBM, used to say, you've heard 3 people can keep a secret if 2 of them are dead, Benjamin Franklin. He amended that to 3 people can keep a secret if all 3 of them are dead. It's because it's very easy to trick a user out of a secret. It's so incredibly easy to do that, it happens all the time. So if the user simply can't release his own secrets, that's one way of keeping them secure. And the TPM can be used that way. And of course there are what we call migratable secrets, and the name's a bit of a misnomer, because normally when you think migratable, you think that the key can only be here or there. And by migratable, we really mean duplicatable. That is, you can make that key usable on multiple platforms. And that's a really useful thing when you talk about being able to upgrade a system. The way we've designed this, as you'll see, is we've got one key at the bottom that you can move, and then you put most of your keys on top of that one. And then when you want to upgrade your system, all you have to do is migrate that one on the bottom across the new system, and all the others just immediately follow. And that makes it easy for people to buy a new device, which, as you understand, when I was working for the PC company, it was very important to me. So these storage keys can be used as key encryption keys for any type of the other kinds of keys, signing keys or keys that encrypt symmetric keys and things like that. We're going to see that in a minute. So here are the storage keys. And our storage keys, we figured storage keys are going to be sticking around for a while, so we need to make sure they're fairly strong. So we mandated that their key length be at least 2048 bits. Well, TPMs being cheap devices, that means that also means that their maximum size is 2048 bits. We had a bunch of people telling us, you're crazy, that's way too big. Only the military use 2048 bits. You don't need to do that. And we said, these things might be around for 20 years. We've got to make them as strong as we can. So we mandated they'd be 48-bit RSA keys. And they're used for 2 things, as key encrypting keys, or to do something we call sealing, which encrypts small amounts of data, like could be used for a 256-bit AES key, to that key, and it will allow you to decrypt that under certain conditions. Then we have two other kinds of keys, signing keys and binding keys. Signing keys can only be used to sign data, and binding keys are only used to encrypt small amounts of data. The difference between a storage key encrypting small amounts of data and a binding key encrypting small amounts of data is the binding keys can be migratable, and not just migratable, but you don't need to use the TPM to encrypt data with a binding key. The encrypting uses the public key operation, and so if you know the public key, you can be, off in Afghanistan and encrypt a little bit of data and send it off to the TPM that knows the private portion, and it can decrypt it. Storage keys won't let you do that. To encrypt things with a storage key, you have to talk to the TPM that knows the private portion of the key. And that's because they keep a little bit of history that proves that it was encrypted at the time that the TPM was in a certain state. And so, if you're not talking to the TPM when you do that encryption, you can't have that history be believable. And so, if you use a storage key to encrypt small amounts of data, you have to be talking to the TPM itself. If you use a binding key, you don't have to be. So binding keys are a little more useful than storage keys that way. And then you've got this other kind of key called an attestation identity key. These things are automatically non-migratable in 2048-bit RSA keys. Again, in 2.0, we relaxed that. But these things will only sign things that the TPM knows itself to be true. So that is, it'll only sign things that are referencing data that the TPM itself has. So things like its platform control registers, which we'll talk about in a minute. It'll sign a certificate that says, this other key that I've got loaded in my TPM right now is a non-migratable key. TPM knows that, so the AIK will sign that. It will sign something called a tick count. That is a little clock that's running inside the TPM. Not really a clock, because every time you turn off the TPM, it goes back to 0. But it'll sign something called an audit value to tell you how many times a particular command has been used in a TPM and data that was used with it. I say it's available because, as far as I know, the only time it was ever implemented was in an emulator. Okay, so let's talk about platform configuration registers. There are 24 DRAM locations on a TPM 1.2. Okay, they each have 20 bytes long. This gets replicated in 2.0, except they don't have to be 20 bytes long because you might be using a different hash. Generally, they're only writable via something called an extend operation. And what an extend operation means is it starts with a value of zeros. And if you want to change the value that's inside there, you give it a value. It appends that value at the end of the zeros that you started with. It hashes the result. And then the result is 20 bytes long, and it replaces what used to be there with the result of that hash. So this becomes a one-way function. So you can change it from zeros to something, and then to something else, and then to something else. But unless you can reverse the SHA-1 hash, you'll never be able to get back to zeros. And that part of the SHA-1 hash is still secure, in my knowledge. They do have a PCR 16 in particular, that is resettable back to 0. And I insisted that we put in a PCR that is resettable back to 0, because if you're writing a program and you want to see if it works, having to turn off the PC every time to test this thing just becomes a real annoyance. So we've got one PCR that's used for testing. So you can set that one back to 0, and that is really cool if you want to show that things are working. You can reset that PCR to PCR 16 back to 0. So some of the PCRs are used to record the boot history of the PC. Now, the TPM itself doesn't know what's going on in the PC at all. So it's not watching. What's happening is you've got another piece of software out there. In particular, it starts with the BIOS. And the BIOS has this cool transitive chain of trust. And what it does is, it first of all extends itself into PCR 0. Nobody's really sure why, because of course if it's been hacked, you can't trust what it's extending, but it does it anyway. And then what it does is it takes a look at the rest of the BIOS that hasn't run yet, and it extends the rest of the BIOS into PCR0. And then it jumps to the rest of the BIOS and lets it run. Okay? It extends the configuration of the BIOS into PCR1. It extends the option ROM into PCR2 and the option ROM configuration into PCR3 and the MBR into PCR4 and the MBR configuration into PCR5. And the whole point is before anything runs or is used, it gets extended into a PCR. So if something is not trustable, it doesn't get a chance to fool with its own measurement. So at the end, if you look at all the PCRs and say, yeah, they're what I expected them to be, then you can be sure that they represent code that really was what you expected the code to be. Can't go backwards because this is a one-way function. Okay, and kind of a neat little thing is that the even PCRs represent code, and the odd PCRs represent configuration. And that's kind of cool because what you can use these PCRs for, which hopefully is on the next slide. Okay, there are a couple things you can do with PCRs. One, you can have the TPM attest to what the PCR values are. Remember that AIK that I talked about? It can only sign things that it knows are true. One of the things it knows is true are the actual values that are stored in those PCRs, because it can see. It's inside the TPM, it can see the values that are inside the TPM. So it's willing to sign those values. So you can ask the TPM, what are the values of your PCRs? And it can answer. And when you ask the question, of course, you give it a random number, and it signs the PCRs along with that random number and sends that back. And the reason it does that is so you can be sure that it's not a replay attack. It didn't answer that question 10 days ago, and now it's just replaying that answer it gave you 10 days ago. Can't do that because you just gave it the random number 5 seconds ago, so if that's a part of the signature, the answer must have come back within the last 5 seconds. Okay, so some people got really, really worried about, oh no, this TPM is going to be having the possibility of sending back information that if you could figure out what it meant, would tell you what was running on this computer. That's kind of a strange worry for several reasons. One is, every PC is so freaking different. I don't know anybody that can figure out what those PCR values are. What you can figure out is if they've changed. So you measure them when you first get the device and get it set up, and then you check it again every time after that to see if they've changed. That actually makes sense. But even if you get two PCs of the same model from the same manufacturer set up the same way, the PCRs may not be the same. I've not figured out precisely why that is, but I think it's because the option ROMs may be a little bit different, even though it's the same model, because they source from multiple suppliers. So being able to figure out something from those PCR values is actually not a realistic privacy problem. But just because people were worried about that, we were worried about that, and so the TPM doesn't come with any of these AIKs. You've got to generate your own. When you generate it, you can give it a password, so it can't be used except by you. You can't generate them except with the owner authorization, which you have to set yourself. And the only key that comes with a TPM when you first buy the TPM is something called an endorsement key. And then people got all worried about this endorsement key. Oh, won't that endorsement key be a privacy problem? Well, the endorsement key is handicapped. That endorsement key can't be used to sign anything. It can't be used to encrypt anything. The only thing, well, there are two things that it's used for. One is to pass in the owner auth password when you first turn on the TPM, because You might be worried that somebody's listening in at the device driver is listening as you give it an owner authorization. Well, you encrypt it with the public portion of the EK, and they can't do that. Okay, that's one thing it's used for. And the second thing it's used for is to decrypt AIK certificates. After you create an AIK, you pass in a certificate for that AIK along with the AIK. The TPM checks to see, is that indeed an AIK that I generated that's inside here? Oh, yes it is. Therefore, I will release a AES key, for example, that's used to decrypt the real certificate for that AIK. So it's a very obscure protocol that's used to prove that that AIK really did get generated inside a TPM. And it can only be done by somebody who knows the owner auth. So this thing is really privacy secure. Okay, so again, remember the cost issue. We don't have a battery in the TPM, at least not usually. Theoretically, somebody could put one in. I don't think anybody ever has. But we do have a tick protocol, and every time you turn on the TPM, it generates a random number that gets associated with this tick. And so if I ask it what time it is, it gives me two things. It gives me that random number, and it gives me the current tick count. We'll see how that can be used in a minute. We've got something called a monotonic counter. There are 4 of them, but you can only use one at a time, one per boot sequence. It can be incremented, and you can ask it for what its value is. And that's about it. I think we finally figured out something that could be used for involving virtual TPMs, but it took a very long time before I figured out any use for this thing. There's something called direct anonymous attestation for those people who thought that the AIK protocol was obscure enough. The DAA protocol is very complicated mathematically. I had somebody explain it to me once, and after an hour I understood it for about 5 minutes. I don't understand it anymore. I don't think it's likely ever to be used, but it's a means of proving that a key came from a real TPM without there being any possibility that you can figure out which TPM it came from. Okay, so now when we authenticate to a TPM, you want to use a key, for example, you have to authenticate to the TPM to say, yep, I'm who I say I am, so you can go ahead and use me. So the main way you do that is with an HMAC. So that is, it's like a password, except you tell it, this is the command I want to do, here's a random number the TPM gave me, and I take that plus the parameters I'm using for the command and my password, and I hash them all together. It's a little more complicated than that, but it's approximately that. You hash them all together, and you send that in for your authentication rather than just passing the password in. There is a means of using something called a ticket for key migration, and the ticket is valid all the time. After it's created, you can continue to use it. And the reason we did this was if you're an IT organization, you might be willing to say, I'm willing for you to migrate, that is, duplicate your keys to another public key, move these keys to my backup storage, but I don't want you migrating them in just anywhere. And so with the owner auth, you're able to create a ticket that says, this is your only target of duplication or migration of keys. They can only go here. Now, just because you've allowed people to go to another location doesn't mean that they will go to that location. And it doesn't authorize keys to be migrated to that location. It's one of 2 authorizations that are necessary. The owner of the key also has to authorize moving that key. So you've got split authority here. PCRs can be used for authentication. That is, those values that are in the PCRs, you can lock a key so that that key can only be used if those PCR values are what you think they ought to be. And if they aren't what you think they ought to be, the key can't be used. Now this means that you don't have to go through this long protocol of asking the PC, "You in a good state?" "Well, here's my state," and then look and see if that state has changed and say, "Okay, you're in a good state. You can go ahead and get on." You can just say, "Can you sign with the key?" You can, you're in. And if you take a look at things like WPA2, what do you use to get in? Can you sign with a key? You can get in. So it's pretty easy to kind of short-circuit a lot of the protocols by locking a key to a PCR. And there's some other cool things you can do with that, which we'll see in a minute. And then there's something called locality. This is something built into AMD and Intel chipsets, and that's used for launching hypervisors and making sure that the launch of the hypervisor was measured correctly. It's sort of a way of putting your system back into a clean state and rebooting without actually turning the machine off. So here's a little animation showing, first comes, there's an EK in this chip. Let's see if I can point to that. So the only thing that's in this chip when you buy it, maybe I ought to put it up here. Yeah, you got an EK. That's it. It's got some PCRs, but of course there's nothing in them. It's got a random number generator. It's got an RSA engine. It's got a SHA-1 engine. It's got a tick. If you turn it on, it'll have tick nonce. It's got some firmware in it. It's doing all these commands, and it's got some DRAM. Okay, so I put in an owner auth and an authorization for the storage root key. This is the key that we're going to use to encrypt all the keys that are outside the TPM. We used to call it a root storage key, and then somebody pointed out that the acronym was RSK, which spells risk. So we thought that Shark was a much better acronym, so we call it a storage root key instead. So you input that into your TPM, and it generates, using the random number generator, generates the Shark. And it also generates something called TPM proof, which is its own random nonce that it's going to use to prove to itself that it generated something. That TPM proof never comes out of the TPM, it's just something it uses itself. And we used that EK, that was the only thing that was in there, to put in that SRK auth in the owner auth. We used the public portion of it. We encrypted those two authorizations with the public portion of the EK, and the TPM then used the private portion to decrypt it. Okay, suppose we want to create a signing key. The SRK is a storage key, so it can't sign because it's a really bad idea to have the same key be used both for signing and for encryption, because those are opposite operations. So what you do is you create a key object template, and you tell the TPM, you're going to tell the TPM, this is the kind of key that I want you to create. So you're going to tell it the type of key. It's going to be a signing key. You're going to tell it the authorization data that I'm going to use, what password I'm going to use for my HMAC calculations. If it's going to be a migratable key, you'll give it a migration password as well. If it's not going to be a migratable key, you won't do that. If you want to lock it to PCRs, then you'll tell it these are the PCRs and these are the values I want you to lock it to. Generally speaking, nobody does that. And then you give it blanks for the private key and the public key, because you're going to ask the TPM to use its random number to do that. So you send that all into the TPM, and it fills in the blanks. Okay? And then it sends it back out, but now you see it's got a green border. And the reason it has a green border is basic. Oops! Let's see if I can go back. How do I go back? Little green button. There we go. The green border means wrapped with the SRK. And actually the only thing that gets wrapped with the SRK is the private key and bunch of other things like all the authorization data, all the stuff that you don't want anybody to be able to see from the outside. But the public key isn't wrapped, and actually the PCR that you're locked to isn't wrapped either. But a hash of all the stuff that's outside is also stored inside, but that's probably neither here nor there. Okay, so now we're going to talk about key hierarchies. By the way, I've got, what, 15 minutes? Perhaps I ought to move up a little quick. So you can have, you can create a key object outside, a root migratable storage key, like I mentioned before. This is wrapped with the SRK, so it's got a blue border. Then I can tell it I want to sign it. Whoops, let me go back just real quick. Let me try to go back. Okay. So I want to create a signing key. So the first thing I got to do is I got to put the root key in there so it'll know how to wrap this key after it creates it. So it creates this key, wraps it with the root migratable storage key. Since the root migratable storage key is orange, I've got to use an orange wrapper. And I can make an AIK key. That's not going to be migratable, so it goes right underneath the SRK. And I can make another migratable storage key if I want. And here's the signing key. It's going to be underneath this new storage key that I created. But now to get to that storage key, I first got to load it. To load it, I got to load the root migratable storage key. So I load both of those so that now I'm ready to create this one. So you get these chains of keys. Now if I want to upgrade my PC, somehow I got to take all of these keys and move them to my new PC. And to make that easy, first I make a ticket that says it's okay to move this key over here. So I use the owner auth to tell it it's okay to move to that location, and that's a ticket. And then I go ahead and give the authorization to migrate this one to that key using this ticket, using the authorization, and here it goes. I put all that stuff in, the TPM says, okay, I'll let you move over to the new TPM. And as soon as I moved over to the new TPM, well, the new TPM now knows how to unlock all the rest of these things because they were already stored with the orange. So you only needed to migrate one key to migrate all the rest of your keys, and that's really cool. Now you couldn't migrate your AIK key because you were using that to prove it was this particular PC that had these particular properties. And if I could migrate that one, it would break the whole use of the AIK. So I have to generate a new AIK in my new PC. That shouldn't be that big a deal. These migratable keys can also be created outside the TPM because you can migrate to any public key, so you can actually, if you know the public key, you can create a key and wrap it with the public key. The TPM doesn't know whether you've done that or not. So you can do that, and that's kind of cool. I'm going to start moving a little faster if I can. Okay. Any non-migratable storage key can seal data up to 153 bytes. We had to make sure that it was at least 256 bits, and 153 bytes is certainly that. So basically, you pick the PCRs and what values they're going to be in, and then you give it a key that you wrap with the storage key. And the biggest use for something like that is something like BitLocker, where you say, I'm going to allow you to decrypt this storage only if nobody has inserted a bootkit into the system. And that's a really good use for that kind of thing. Binding data just encrypts with a public bind key, so no PCR values are being locked together with that data. However, since it's a key, you could lock the binding key to PCR values if you wished. And that's kind of cool because if I'm on a remote system and I want to give you data that you can only decrypt if you're in a good state, I don't have to talk to your TPM and do a seal. I can create a bind key that will only decrypt if it's in the correct state, and then I will bind data to the bind key, send the whole thing over to the TPM on your system, and your system will try to use it, and if it can use it, then you're in a good state. Okay, so here's some weird things you can do with TPMs. Okay, so there's a migrating 3-step. Before we talked about the migrating 2-step, where you needed two things. You needed the ticket, and you needed an authorization value, a migrating key from here to there. Now, if I am worried that my motherboard is going to go south, and I'm going to lose all my keys because my motherboard went south, I might want to migrate my key before my motherboard goes south. So I'll migrate my key to your system. But maybe I don't trust you. Maybe you're going to take all the trouble of polishing down your TPM to get to its secrets. Somebody did this about 3 years ago, one of the black hats. It cost $250,000 and they ruined, 17 or 18 TPMs, but they managed to get the secrets from one TPM doing this. So maybe Kinko's is offering a service that will back up your TPM keys, and I'm willing to go ahead and use Kinko's to store my keys, but I'm just a little bit antsy that maybe Kinko's is going to have a bad employee in there trying to get everybody's keys. So you can do something I call the migrating 3-step. And rather than go through all the slides, let me just tell you, when you tell it to migrate, you can tell it, by the way, here's a random number. I want you to encrypt the inner blob with this random number, with this inner encryption key. And I'll write down this inner random number on a piece of paper and put it in my safe. Now I'm going to ask Kinko's to migrate it to my new computer. They migrate it to my new computer by rewrapping it with my new TPM 2. But it's still, the inside is still encrypted. So now what I can do is I can pass in the, go backwards. Okay, I can pass in this random number that I got out of my safe into my TPM, and it will undo the inner encryption, and then send it back out encrypted again with my TPM. So the key never actually got decrypted outside the TPM, and even if Kinko's had managed to decrypt that system, unlayer that TPM, and gotten to the insides of it while they were storing it, all they would have gotten was an encrypted blob, so it wouldn't have done them any good. So, not to say anything bad about Kinko's, it was just an example. Okay. So it's just showing that if you could get to that, then you could decrypt all the keys, not just that one. So yeah. Okay, with a tick stamp, you can actually do a timestamp if you've got a trusted time source, and this explains how to do that. Since we're running out of time, we're going to just skip through that. You can timestamp a nonce, and the reason you might want to timestamp a nonce is it proves that anything that includes that nonce was generated after the nonce was generated. And so if you timestamp the nonce, you know something took place after a certain time. Seal's kind of cool because it's difficult to pass data back and forth between the pre-boot system and the post-boot system. But here you've got a piece of NVRAM that both of them can see. And another neat thing about the seal is, you know when the system first booted, what are all the PCR values? They're all 0. And after you finish booting, none of them are 0, or at least 0 through 5 aren't 0. So if I seal something to the PCR values being 0, then I know that it can only be decrypted and read in the pre-boot state. So it gives me an easy way for the OS to pass data to the pre-boot state that only the pre-boot state can read, which is kind of cool. I really like the multiple users on one system, though. You take PCR 16, and you've got a user, he logs in, and he extends his password into PCR 16. And he locks his keys to PCR 16 being in that state. Okay, as long as he's logged in, he can use his keys. Now he logs out, all he has to do is reset PCR 16. It's now all zeros, none of his keys are usable. Next person logs in, you don't have to reboot the system, he just logs his password into PCR 16. Now he can use his keys. When he's done, he resets PCR 16, the next user can use it. I think that's pretty cool. Time lock of data. It takes a while to extend a PCR, so if you extend it many times, you can say it's going to take a while to get to the point where you can unseal the data. This explains how you were supposed to activate identity. It's a fairly complicated procedure, and I'm not going to go through that, but here's some other cool things you can do with Activate Identity. Instead of activating identity, you can use the EK to pass data that will only be decryptable on a particular PC that you know the EK for, as long as you also know a public key of an AIK that's on that PC. If you know those two pieces of data, I can encrypt it with the EK, and only the EK will think it's doing an AIK certificate creation process, and it will decrypt that AES key for you. The grocery card passing to anonymous AIKs from the CA. Y'all have these grocery card things that you use whenever you buy groceries to give you a discount? Grocery stores use these things to keep track of everything you buy, so they can give you targeted coupons. Well, a bunch of people decided that they didn't want people to know what they were buying, so they formed little clubs and they started trading the cards around. So I'll use this card today, and I'll use that card the next day. But you can do something very similar to prevent anybody from knowing what your EK is when you're asking for AIKs. What you can do is you can make a whole bunch of requests for a certificate from a CA using a whole bunch of EKs, only one of which is actually accurate and valid. And you get all the responses back, and the one that's valid you use and get a certificate for your AIK, but the CA doesn't know which one, so they can't. The CA, even if they cheat and try to keep track of which EK belonged to which AIK, they can't. So that's kind of cool. Got 2 minutes. When you're activating an identity, turns out the protocol looks like you have to first activate your identity, and then you can use your identity to activate a credential for your SRK or for signing keys or for other things. And it looks like it's a fairly long protocol to get all the certificates you need. Actually, that's not the case. You can do it in one swell swoop, as they say. You can ask it to certify everything and have all of the certificates be decryptable and valid, or none of them be decryptable and valid in one fell swoop, and you can read the process for doing that here. NVRAM has some cool things you can do with it. There is NVRAM on the TPM, and it has the same controls as keys. So you can use the NVRAM. You can have NVRAM that's only readable if you know the password, only writable if you know the password, or read-writable if you know the password, or readable by anybody, but only writable by you, which is a cool thing if you've got a public key that you want to make sure that nobody changes, like maybe your root public key of your Internet Explorer or your Firefox. You might very well want to store that in some place where nobody can mess with it, but you can use it. However, before the TPM is even owned, you can write to this NVRAM exactly 64 times. After that, it's locked. The reason for the 64 times is we were worried that somebody was going to write a piece of software that was going out there just trying to destroy TPMs And you all probably know that most NVRAM, after it's been written 100,000 times, it's dead, approximately, just burns out. So we limited you to only being able to write it 64 times before you take ownership of it. So you might be able to do something like that when you're manufacturing PCs and you want to make sure that something is, we finalize this, it's ready to go. You can kind of lock it by writing this NVRAM 64 times and it can't be erased until somebody takes ownership. And then you can put owner evict keys, so-called, because the owner auth is required to do this. You can take a key that you've generated and told the TPM, please remember this, don't forget it when you turn off. And that's really cool if you've got through stock, field replaceable units, you got a motherboard that you want to replace into one of your company-owned PCs, and you're using your VPN as linked to a TPM. You don't allow anybody to log into your company unless it's a company-owned system. That makes a lot of sense. You don't want somebody from Romania or whatever logging into your system if you don't have anybody in Romania. Okay, so as a result, if you're going to replace a motherboard in the field, how do you get that machine to be recognized by your VPN? Well, the easy way to do that is to put a key in the motherboard replacement, and you can do that by putting the key, generating the key in the motherboard, telling the TPM, remember this key, and then when you replace that key in the machine and you turn it on, it already has a key in it that your IT infrastructure recognizes. So there have been a lot of things that have been suggested that can be done with NVRAM. I think a lot of these are more appropriate to use with Opal drives. These slides were made before Opal drives existed. You could actually put your entire BIOS in NVRAM. That was suggested in a paper written by somebody in China. You could use it for covert channels, which is why you don't want to use the same TPM for different virtual machines, because that would give you a place where one virtual machine could store data and then a different virtual machine could read that data, and that's not something you want to do. And you could also use it as a way of stuffing data between the OS and the BIOS, the preboot area. The TPM also allows you to set up a tunnel between you and the TPM if you're really worried that there might be some bad guy listening in at the driver level. Like, for example, you're talking to your machine that's at your home and you're at the office and you want to make sure that your communication channel is really secure. And you can do that by creating a tunnel between you and that TPM. The problem might be we need a shared key to set up a tunnel. So how do we set up a shared key? And the shared key is set up using authorization data. And so the SRK, which is the public key you probably know, typically doesn't have any authorization data. It's either set to be a no-auth key, where it really doesn't have authorization data, or it's set up to use the well-known secret, which happens to be 20 zeros. If you're going to use a well-known secret to establish your secret key, that's not going to work very well. So instead what you do is you create another key, you wrap it with the SRK's public key, you put this a new authorization value as the authorization value for this key you just created. You pass that to the TPM. The TPM loads that and says, oh, so that's what the authorization data is, and then use that authorization data to set up your tunnel. One of the coolest things about TPMs that, as far as I know, nobody has used, and I'm just waiting for somebody to come up with a use for this, is there are GPIOs on the TPMs. Even some of the ones that are manufactured. I think Infineon has 2 or 3 of them on their chip. And these GPIOs can be turned on and off using the same controls as the keys or the NVRAM. You can hook this up to a door lock, or the lock on your PC system or whatever, so you can only unlock your PC, physically unlock it, or unlock the door with the correct authorization. By the way, the authorization of the TPM is a lot more secure than the authorization of just a normal password, because the TPM keeps track of how many bad authorizations that you make. If you try to authorize this thing with the wrong password too many times, it's going to say, I'm done for a while. Come back in a certain amount of time and I'll let you try again. And by doing that, it prevents hammering attacks. You can't just start guessing passwords until you get the right one, because there's this delay in there. I know in the first TPMs we had some that actually went up to like 24 days. Delay, it was an exponential increase until it got to be really long. The TPM 2.0s have a standard way of doing this. It's called leaky bucket, where you've got a bucket that can contain a certain number of bad guesses. Once you have filled the bucket, it's going to stop until some of the bad guesses fall out of the bucket. And they fall out of the bucket at a regular pace, and the bucket is a certain size, and what the size and the pace at which they fall out will be defined by the PC client specs, so I don't know what that's going to be. But it's a very easy way of preventing somebody from hammering attacks. But do the calculations. You can find out if the bucket is 100 guesses, and it takes an hour for it to leak. It's never going to fill up unless somebody's hammering. And you don't want it to break if somebody's hammering. So that's really cool. That's a way of turning a weak password into a strong password. You can use these GPIOs for an LED light. There are all sorts of cool things you can do with a GPIO, and I don't know why nobody is using them yet. But I think that'd be really cool. I personally, one of my challenges I'd like somebody to design is I would like my PayPal account to only be usable from these 5 devices. To get to one of these devices, you have to break into my house. And I want this device to actually provably have me in front of it. Or at least somebody in front of my device to use my PayPal account. So somebody actually has to physically break into my house in order to use my PayPal account. And I don't think that's impossible. I think that's quite possible. But nobody's done it yet. You can proxy passwords with biometric devices. Now with 2.0, you can use extended authorization to do this really easily. But even in 1.2, you could create a biometric device that would do the HMAC so that nobody in between could spoof you. And you'd actually have to physically spoof the device in order to authorize a key. And if you could do this, that would solve my previous problem of how do I make sure that my PayPal account can only be used if you break into my house. Because you'd have to physically put a fingerprint across the fingerprint reader to get it to work. Printers. Suppose I had a TPM and a printer, and I put the public key of that TPM in my device driver. Then when I print something to the printer, I could easily encrypt it so only the printer could read it. And then I don't have to worry about somebody sitting on the line in promiscuous mode reading all the PDFs that are being sent to the printer to be printed. That'd be really cool. By the way, one of the biggest uses of TPMs today, anybody know what it is? It's in Las Vegas. That's true. Using a CA for an internal radio server, it would be one of the biggest problems with PKI, as far as I can tell, is you say anybody whose key has been signed by me is okay, but you don't have a list of the keys that have been signed with your private key. And if somebody's broken into your system surreptitiously and managed to sign a couple extra keys, how do you know? So you don't have a list. Well, with the audit feature of TPM 1.2, you could actually have a list of all the times that TPM was used to sign something. So you could actually have an auditable list that would prove what things that CA had signed. That would be cool. Okay, so I guess we have a little bit of time for questions. Please step up to a microphone if you have a question.
This isn't too terribly technical. You said that the primary use for TPMs right now is in Vegas. Do we see
Gambling machines. Yes.
Huh?
Gambling machines actually use TPMs.
Do we see TPMs in use in voting machines?
No. Wouldn't that be cool? I've seen some papers. And I think that would be a really good place to put TPM, because I'd really like to know that my voting machine has the software on it that was supposed to be there. I think Russell Fink has written some papers on using TPMs in voting machines. It'd be really cool if somebody did that. I don't want to say that nobody's using them out in the real world, because obviously PricewaterhouseCoopers is a good example. I've forgotten how many they used. 80,000 was it? 80,000 they're using for VPN authentication, and they're certainly not alone. It's just one that's allowed their name to be used. For some reason, people don't like to broadcast what defenses they're using against the hackers. Any other questions? I know Wave Systems has sold a lot of people software that's being used to use TPMs, but I don't know if they're willing to tell anybody who they are, other than PricewaterhouseCoopers. Yeah, I was afraid of that. Okay, well, thank you very much, and I'll be around.